This is Britt Caswell with another example video. In today's video, I'm covering example 1 from section 5-3 in the SavvasRealize Algebra 2 textbook. The goal of today's example is to graph square root and cube root functions. So I've actually done this a little bit differently in that I already produced the graphs and put them on Desmos. So what your textbook does is it actually shows you how to do it with a table of values. Okay, but I wanted to show you some of the key features that are important here. So they were looking at the square root of 3x, and so you might be wondering why they picked these specific numbers or how they picked them. What they were doing in picking these specific numbers is they were finding things that would cause this to become a perfect square. So for example, 3 times 0 is 0, and that's a perfect square when you make it, or when you do the radical part there. 3 times 3 is 9, which again is a perfect square. Here, 3 times 12 is 36, all right, and 3 times 27 is 81. So they're picking these values based off of the fact that they make that perfect square. And so you know that you have a square root function when you have kind of this swoop right here. Now, if I were to mirror this across the axis here, very roughly mirror because I don't know how to draw. And if you turn your head to the side, you can see that this is actually just half of a parabola that's on its side. Okay, so that's what you're kind of looking for with these square root functions. Now this here is a cube root function. Okay, notice that it's almost like a cubic function that's been it's been reflected. So, right, the parent cube root function looks rough, or cube function looks like that. And so if you reflect it across the line, y equals x, which is this roughly dotted line, that's how we're getting the cube root, okay? When we get into inverse functions, you'll see why that reflection occurs. But just understand that if you guys know that, like if you guys know the inverse operation of your root, like the cube root or the square root is a square, then just you can reflect the parent function over. So cube root functions, they have like this distinctive S shape. This one's been compressed, so I can't really show you on this one the what I call the Orion's belt, which is usually these 3 points. I'll be showing it to you on the next graph. But usually that's kind of what I look for, is what's called the Orion's belt. And I do it on both of these. So yeah, so let's go ahead and let's take a look at some of the questions here. It says, what are the domain and range of the function? Alright, so our domain in this case, remember, is all of the x values that the graph passes. So this is starting at 0, 0 and going to the right. So it's x is greater than or equal to 0. And our range starts at 0, 0 and goes up, so it's y is greater than or equal to 0. And if we talk about increasing versus decreasing, you can see that this graph is going uphill the entire time. So it's an increasing graph. And that kind of makes sense, right? The bigger of a square root that you're taking, the bigger the number comes out, right? The same thing works with cube roots. The bigger number you're taking a cube root for, the bigger number that comes out. Now this one, when we go to talk about the domain, this graph continues for forever to the left and forever to the right. So our domain in this case is all real numbers, which I write using that funky little r. And the range is where kids tend to struggle on this graph. When they look at these ends, they see them going left and right, But they don't realize that this one's still kind of going down a bit. And this one's still kind of going up a bit. So just because they go up and down slowly doesn't mean that they're not going up and down, okay? So this graph continues to increase for forever and it continues to decrease for forever. So the range is also all real numbers. Alright, so now let me show you kind of what I mean about the Orion's belt stuff and remind you about transformations. So if you've seen some of my other videos, you've seen this part, okay? So with transformations, it behaves the same on all functions, okay? You've seen this probably where this has been squared instead of a root. All right, you might have seen it cubed. You might have seen it as an absolute value. Okay, but they're all the same. So if you're doing something outside of the grouping symbol of the function, such as a, which is multiplying, and k, which is adding, you are doing some kind of vertical change. If you're doing something to the inside of the grouping symbol, you're going to have a horizontal change. So now let's talk about a. So a is multiplying to the grouping symbol. And so that a has three jobs. If it's negative, you're going to have a vertical reflection. If the number for a is bigger than 1, you're going to have a vertical stretch. And if the number for a is between 0 and 1, you're going to have a vertical compression. Alright, so that's in charge of stretches, compressions, and reflections. Now these other two, the h and the k, they're being added and subtracted, okay? So when you add or subtract from a function, you're going to get some kind of translation. Now, if that translation's horizontal inside the grouping symbol, you see there's a minus in the equation? That means that it's going to make your numbers feel backwards. So if it says minus h, you're going to feel like you need to go to the left, but really, you're going to go to the right. And if it says plus h, you're going to feel like you need to go to the right, but really, you're going to go to the left. The vertical translations are how you feel like they'd be because it's already added in the equation. So if it says plus k, you go up, and minus k goes down. So now let's apply this to our functions. So I'm going to start with my parent function, okay? So on part A here, I have a square root. And so with square roots, I know the square root of 0 is 0, square root of 1 is 1, square root of 4 is 2, and the square root of 9 is 3. Okay, so I just go down my list of perfect squares and take their square roots. That gives me that nice swoop there. So if I look at my function here, the only thing that's changing is there's a minus 5 here. So it's inside the grouping symbol, so it's a horizontal change. It's addition or subtraction, so it's a translation. And minus 5 takes you to the right by 5. So if I take all of these anchor points and scoot them to the right by 5, you get this new swoop for your graph. Now notice on the endpoints here, I kind of goofed there, I should put an arrow. There will be an arrow on this endpoint, but there's not an arrow here, right? Because you can't take a square root and get a negative number. So this can't keep continuing to that left downish direction because it's undefined. That takes you to the imaginary zone. Alright, now let's talk about b. So b is a cube root function. And so you guys heard me talk about the Orion's belt. So I'm going to go ahead and draw it in there. So I refer to that as the Orion's belt because they're all one unit away from each other. Cube roots grow very quickly, right? Like 0 cubed is 0, 1 cubed is 1, 2 cubed is 8, and 3 cubed is 27. So at most, you tend to get the cubed root is 8, which isn't even on this graph, because most graphs don't go out to 27. So this is going to roughly look like this. Very roughly, because I shouldn't have passed the 2, but you get the general gist of the shape, okay? So now let's talk about the transformations happening to it. So here we're adding 1. So again, addition and subtraction in the grouping symbol is a horizontal translation. But when you add 1, you're going to go to the left. So if you take your Orion's belt and scoot each point to the left by 1, you get a graph that looks roughly like that. So there we have it. That's how you graph like the parent function and some of our transformations on square root and cube root functions. Until next time.